Hi everyone. All right, so for this lesson, we're really going to focus on graphing inverse trig functions. So we're going to kind of take a step back and we're going to kind of do a little throwback. So we're going to focus on just doing the inverse of just this function here to start off with. So this function that we have here is just your parabolic equation y equals x squared. So the graph kind of got cut off a little bit, but you can put arrows on the ends. So the whole premise of inverses is I want to reflect it over the line y equals x. So with the line y equals x, we're going to reflect our graph over that line. So another way to kind of approach this is what you're going to do is you're going to take your coordinates and we're going to flip the x and y, and we're going to graph those new points. So if I were to take the point -2, 4, that's going to become the point 4, -2, and then that point would be located down here. So I'm going to put that point right here. And then the next point that I want to take the inverse of is going to be -1, 1. So that's going to flip and become 1, -1, and that's going to be right here. And then of course we have 0, 0, which when you flip it, it's still going to stay right at the origin. 1, 1 is going to flip and stay right where it is. And then we're also going to have the point 2, 4, and it's going to flip and become 4, 2. So your inverse will look just like this. All right, so that being said, now we're going to look at the domain and range of these two things. So we're going to look at the original function, and then we're going to look at the inverse. Now, what I want you to kind of notice is down here in this box where we have f of x and we have the inverse, if we label the inverse as just inverse, as in like the English text inverse, then that tells us that it doesn't have to be a function, meaning it doesn't have to pass the vertical line test. So we're just going to take the value as is, or what we see. So when I take the domain, I'm going to do the original. So I'm going to do the original here in blue. Okay, so the original domain is going to be all real numbers. So from -infinity to +infinity. And then my range is going to go from 0 to infinity. Now my inverse, the domain and the range are going to flip from the original. So now the domain of my inverse is going to be from 0 to infinity. And then the range is going to be all real numbers. So if you remember back from way back when, so another thing to remember with inverses is that when you do your inverse, the domain and range of those values are going to flip as well. So you can also kind of think of it that way. Now, for the next part, number 2, it's really the same idea as number 1, but we change a really small detail, and that's going to be in this table over here. So now we want the inverse function. So because we use function notation and we write it just like this, that means this must be a function. So it must pass the vertical line test. Now in order for the inverse, so I'm going to write this down here. So in order for the inverse to pass the vertical line test, what that means is that your original function, so f of x, it has to pass a different test. It has to pass what we call the HLT, which is the horizontal line test. So if I look at my function up here, so my y equals x squared, so I'm going to go ahead and put my arrows back over here. Go back over it in blue. Yeah, that's terrible. I'm just going to leave it alone. So when I look at my function here, if I try to do the horizontal line test at any of these values, it's going to fail miserably. Relatable. So like here, it's going to fail because it touches multiple places within the same horizontal line. So what that tells us is because it fails the horizontal line test, we have to restrict the domain of the original function. So what that means is we're going to actually essentially just omit or cross out a section of the graph. So the $1,000,000 question we get is, well, how do I know which part of the graph to cross out? Well, in reality, it doesn't necessarily matter. Like we can cross off the left half and then just take the right half, or we can cross off the right half and just take the left half. But what mathematicians have decided is, well, let's make our lives as easy as possible. We like to use the easy values, so we like to use the positive values. So because we like to use the positive values, we're going to cross off the negative values. So this is just the side that we just decided to cross off. So that being said, the only part of the graph that we're going to use is just the right side of this graph. So now the right side of this graph, now it's going to pass the horizontal line test since it only hits it one at a time. Okay, so now I'm going to do the inverse function, and I'm going to flip those points. So I'm going to take the point 0, 0, 1, 1, and 2, 4, and I'm going to do the inverse. So if I flip 0, 0, well, we still get 0, 0. 1, 1 is still going to be 1, 1. Then 2, 4 is now going to become 4, 2. So here is our inverse function. Okay, now down here, so this is f of x and the inverse of f. Okay, so for the original, it depends on the context of the problem, but really f of x here, this is actually referencing the entire function, not just the small section. So really it should be the entire function, but depending on the context, we may only ask for the section that we use for the inverse, but I'm going to use the whole thing for this context right now. So the domain of the entire function is going to be from negative infinity to infinity, but really we're only going to take the part from 0 to infinity. So I'll just actually write both just to be on the safe side. All right, and then the range of my function here, so for the whole thing, it's from 0 to infinity. But then when I just consider the part that I have written, well, it's the same thing. All right, and then when I do my inverse function, so the range is going to be, or not the range, the domain is the range of the original, so from 0 to infinity. And then my range, well, that's going to be the same as the domain of the original from 0 to infinity. So I guess it really is better to just use the portion that we're using for the inverse. That way we have a clean switch, even though really everything's the same. Okay. All right. So moral of the story is if we want the inverse to be a function, we may have to restrict and omit part of the graph in order for the inverse to actually be a function and pass the vertical line test. So that's the moral of the story. So we're actually going to kind of use that logic as we kind of transition into trigonometric functions. All right, so down here, so it's kind of the layout and laydown of kind of the intro and segue into when we actually do the trig functions. So I'm going to kind of give you guys some time to kind of pause here, read through it, kind of take some time and really kind of soak it in. But I don't want to spend a lot of time on it. Otherwise, this video is going to be like 20,000 hours long, which neither of us want. So read through this, pause here, and then I'm going to go ahead and move on. All right, so now we're actually going to find the inverse of these graphs. So we're going to just start with sine of x. So the inverse of sine of x is going to be from negative infinity to positive infinity. But we're going to restrict the domain to a specific value. Now, this part right here, we kind of want to discover. I don't want to just kind of give it to you. I want us to kind of find out what it's going to be, rather. So I'm going to restrict the domain to a certain interval. That way the inverse is going to be a function. So when you write the inverse for sine, there's going to be a couple different ways that you can write it. So we can write it as sine with that -1 up there. So this is, you would still say inverse sine of x. So inverse sine of x. That's how you would say that. And then you could also write it as arc sine of x. So you would say arc sine of x. That's how you would say that. Okay, so now over here we're going to graph sine, and then we're going to determine what the restricted domain is going to have to be. So with sine, know that we're going to, I'm going to put in a scale. So I'm going to do a scale of 1/2, which means every other box is going to be 1. So sine is going to start at a middle point. So I'm going to start at a midpoint, then go to a high point, midpoint, low point, then midpoint. So I want to draw 2 cycles on my graph just to kind of give me a holistic view or a holistic idea of what my graph looks like. Okay, and it connects pretty nicely. All right, so when I look at my sine graph here, notice how when I try to do the horizontal line test, it's going to fail miserably, which, relatable. So we need to restrict the domain so that when I do the horizontal line test, it will pass. But as of now, it doesn't. Sad face. So what I'm going to do is we're going to look for just like parts, like what intervals or like what little sections of the graph I can take for it to actually pass the horizontal line test. So as it turns out, we're actually going to take this little interval here from negative pi over 2 to positive pi over 2. That way, when I do the horizontal line test on just that little section, it passes the horizontal line test, so we're good. So the points I'm going to take for the inverse are going to be negative pi over 2 comma negative 1. Then I'm going to take 0 comma 0, which is this point here. And then we're going to take this high point up here, which would be pi over 2 comma 1. Okay, so what I'm going to do is, or rather, let me scratch that. So that tells me I'm going to restrict my domain to negative pi over 2 to positive pi over 2. So that's what I'm going to restrict it to. So negative pi over 2 to positive pi over 2. And then because I'm including those values in my interval, I'm going to put brackets on these instead of parentheses. So I would only put parentheses if we had asymptotes or anything like that, any sort of discontinuities. Okay, so now before I sketch my inverse, I'm going to kind of point out a few things. So notice how on the x-axis here, we're going to be scaling in terms of radians. But if you look on the y-axis here, I scaled it using just integers. So when you do the inverse, everything kind of switches. Everything's going to flip, which means when I look at my inverse graph, notice how now your x-axis is going to be integers and now your y-axis is going to be radians. So I decided to be a nice person and kind of give you an inverse graph. So yay. Just to make all of our lives a little bit easier, I decided to just kind of give you guys a graph. So what I want to do before we actually get to the graph, I want to make a little quick reference table. So we have x and f of x. So these are going to be the points that I'm taking from my graph. So I'm taking negative pi over 2, comma negative 1, 0, comma 0, and then pi over 2, comma 1. So when I do my inverse, I'm going to flip these points. So x and inverse of f of x. So that means all these points are going to flip. So now I'm going to have negative 1, comma, negative pi over 2, then 0, 0, and then 1, comma, pi over 2. So when I plot these points, so I'm going to have negative 1, so go to here, and then go to negative pi over 2. So it's going to work just like a Cartesian coordinate grid. So I'm going to put my first point here. And then we have 0, comma 0, and then we have 1, comma pi over 2. So notice how your points, they're going to be collinear, meaning they're all on the same line. You could draw a line, but please don't. It's not going to be a straight line. Just know that your points should be collinear, which means they should form a straight line, so it should look like a straight line, but it's not going to be a straight line. So now, the next part, now that we have the points, we need to figure out what the path of the graph is going to go. So we need to determine, is it going to look like this, or is it going to look like this? So we have options. So we're going to kind of discover what it should be. So we're going to go back to the original, and what I want you to notice is here at this first segment of the graph, we're going to look from negative pi over 2 to 0. We're going to look at the concavity. So notice right here how this part would be concave up. So this part is concave up. And then the next part from 0 to from 0 to pi over 2, this is going to be concave down. So just like how when we take the inverse, we flip the points. English is really hard today, y'all. So what we're going to do is we're also going to flip the concavity. So because we start concave up, now in the inverse, now it's going to start concave down, and then we're going to transition to concave up. So over here, we're going to start with concave down. Yes. So now we're going to switch and go concave down and then go concave up. So this is what your graph of inverse sine is going to look like. So now your coordinates that we have here are going to be negative 1, comma negative pi over 2, 0, comma 0, and then we have 1, comma, 1, comma pi over 2. Okay, and then I'm going to go ahead and also label the concavity just to kind of give you a better idea. That way you can hopefully use this page as your reference page if you ever need it. So the first part, we're going to start concave down. And then the second half, then we're going to be concave up. Can I move that up there? There we go. So that's going to be your graph of inverse sine. So now we're going to kind of discover the same idea, and we're going to go through inverse cosine. So with cosine, just the same as sine, your domain is going to be negative infinity to positive infinity. And then once again, we're going to discover kind of what we needed to restrict it to. I don't want to just give it away. So the couple different ways to write inverse cosine. So we have cosine or inverse cosine of x, and then we've got arc cosine of x. All right, so now I'm going to draw my cosine graph. So with cosine, I'm going to put my scale in, so 1 and -1. All right, so we're going to start at a high point. So we're going to start at 1. Then go to a midpoint, and then go to a low point, midpoint, and then high point. Okay, and then on the left side, from a high point to a low point. Nope, high point to midpoint to low point, back to midpoint to high point. Okay, so same idea. We want to restrict the graph so that it's going to pass the horizontal line test. So if I try to do the horizontal line test, it fails miserably, sadly. So what we're going to do is I'm just going to take from 0 to pi. That way, that little segment here is going to pass the horizontal line test. So if I try to do the same segment as sine or inverse sine, where we did negative pi over 2 to positive pi over 2, that would fail the horizontal line test. So I can't take the same interval. So I have to do a different interval where it's going to pass. So as I mentioned towards the beginning, there's really no reason why we can't take like that section or this section, or why we couldn't take this section. But what we decided is, well, what they decided as mathematicians, we're just going to take the value that's closest to the origin and positive when possible. So that's why we're just going to take this interval specifically. So we're going to restrict the domain to just 0 to pi. And once again, we include those values in our intervals, so that would be brackets. Oh no. All right, so the points that we're going to take. So we're going to take 0, 1, and then pi over 2, 0. And then we're going to take pi, -1. So once again, I'm going to go ahead and make my fancy little reference table. So my points I have are 0, 1, pi over 2, 0, pi, -1. So when I do my inverse, so now I'm going to have 1, 0, 0, pi over 2, -1, pi, so on and so on. So now I'm going to plot these points. So we're going to have 1, 0, 0, pi over 2, and then -1, pi. So once again, the points are collinear, which is a good sign, but now we need to figure out the concavity. Okay, so over here, so I'm going to kind of go through this a little bit quicker. So we're concave down in the first part, which means the inverse is going to start concave up. And then we end the original in concave up, which means the original should end, or nope, which means the inverse should end concave down. So we're going to go up and then down. Okay, so over here, we're going to be concave up and then concave down. So this is what your inverse for cosine is going to look like. So your points over here, we're going to have -1, pi, and then we're going to have 0, pi over 2, and then we're going to have 1, 0. And then for your concavity, so I'm going to kind of shorthand this one just to make it a little bit quicker. So I'm going to say C up for concave up, and then for this last part over here, I'm just going to say C down for concave down. Okay. All right, and now for the next part, now we're going to look at tangent. So with tangent, so I'm going to kind of ruin this one a little bit, but or actually here, let's kind of walk through it. So to find your domain for tangent, I'm going to kind of expand it a little bit. So tangent is the same as sine over cosine. Okay, so remember, the one value you can never divide by is 0. So because you can never divide by 0, what that means is cosine can never equal 0. So what I need to do is I want to think about, when does that equal to 0? I want to know what those theta values are. Okay, so those theta values, if I just think about my graph, so I'll let you kind of visualize it up here. So those theta values are going to be like the negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2. Notice how it's all the pi over 2s. Okay, so because it's all the pi over 2s, so let's write this out a little bit more. So like negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, so on and so on. So because those are the zeros, so what this means is the roots of cosine are the asymptotes of tangent. So that tells us that we're going to have asymptotes at x equals pi over 2 plus pi k, where k is an element of those integers. So that's kind of how I think about it. Ignore this down here. We're not there yet. So just focus on this. So this is kind of how I think of it in my head mentally. This is how I can kind of develop a lot of those answers to your questions kind of quick, is because I always think of it in terms of what function is in the bottom, what are the roots of that function, and then the roots correspond to the asymptotes of that specific function. So that's kind of my train of thought. That's kind of how I think it through. Okay, so I'm going to kind of move all this a little bit because I want to be able to work on my graph. So put that over there. All right, so that being said, I know I'm going to have a scale of 1/2, so I'm going to do 1 and negative 1. And then I know I'm going to have asymptotes at those pi over 2s. So I'm going to go ahead and do my asymptotes at all my pi over 2s. So 3 pi over 2, pi over 2. Ding, ding. Okay. All right, now let's kind of do a little quick reference table for you guys. So, whoops. Now, in this quick reference table, I'm actually going to do negative pi over 2 first, because that's where an asymptote is. And then we're going to move to negative pi over 4, which is going to be at negative 1. And then we have 0, which is 0, then pi over 4, which is at 1. And then at pi over 2 again, then once again, we're going to have another asymptote. So let's go ahead and graph these real quick. Okay, so I'm going to go ahead and do 3 full cycles and then the partial cycles on both sides. So I'm going to do this a little bit quicker. I know I'm kind of cheating a little bit, but you know what? That's not fair. All right, and then the partial cycles. All right, so when I draw, I know curving your tangent graphs is a little challenging. Gross. Close enough. Okay, and then down here, we're going to have a partial cycle. Then over here, another partial cycle. Okay, so here's what your graph's going to look like. So now I'm going to go over the points. That way the points are a little bit more clear. All right, so now I'm ready to do the inverse. So if I look at my original, I notice that it's going to fail the horizontal line test miserably. So in terms of the part that we're going to take, I'm just going to take this middle cycle right here, But when I take that middle cycle, that also means I have to take these asymptotes with it. Okay, so we're going to take the asymptotes of x equals negative pi over 2 and x equals positive pi over 2. We're going to take those asymptotes with us when we do the inverse. So when I do the inverse over here, so notice how these are x equals pi over 2's. So I'm going to do the table, and then I'm going to let you kind of discover and see what it looks like when I do the inverse. So when I do the inverse, we're going to have undefined for the x value, but I know the y value will be a negative pi over 2. And then we're going to have negative 1, negative pi over 4. And then we're going to have 0, 0, then 1, pi over 4. And then we're going to have undefined and pi over 2. So here, now what this means is we don't have anything for the x value, which means now we're going to have a y value equal to negative pi over 2. So now your asymptotes are going to be positive and negative pi over 2. That's from here and from here, since we don't have anything in the x values. Okay, so I'm going to go ahead and draw my asymptotes. I'm going to try to, if it works. Here we go. Come on. There we go. So I'm going to have asymptote at pi over 2 and negative pi over 2. Okay, and then for your own little knowledge here, we're going to be graphing some pi over 4s, which your pi over 4s aren't necessarily clearly marked on your axes. So just know that if we have pi over 2 here, halfway between, so here, would be pi over 4. So what I'm going to do is kind of give you an idea of where those pi over 4s are. So let me do y equals pi over 2 for your asymptotes. Okay, and then I'm going to write those pi over 4s really small. So we have, I'm going to write them over here first and then have to shrink them. So that's 1 pi over 4, 2 pi over 4, 3 pi over 4, 5 pi, I forgot 4, counting is hard, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, and then 8 pi over 4. So these are just all your pi over 4s, so I'm going to put these on the scale just in case, but I'm going to make them kind of small so that it's kind of clear which one's which. Whoops. All right, so negative pi over 4 is going to be down here. Positive pi over 4 is going to be right here. So it's going to correspond to these lines that I'm marking. And then 2 pi over 4, which is the same as pi over 2, which is going to be with that orange line. 3 pi over 4 is going to be with this line right here. 4 pi over 4 is the same as pi. So hopefully you can kind of see the pattern. It's going to be every other 2 lines. So 6 pi over 4, which is the same as 3 pi over 2, 7 pi over 4, and then 8 pi over 4, which is the same as 2 pi. So hopefully you can kind of get an idea of what those pi over 4s are like on the graph. All right, so now let's plot those points. Okay, so negative 1 comma negative pi over 4. So that's going to be right here. Then we have 0, 0, and then we have 1 comma pi over 4. Okay, so now we need to look at the concavity. So over here, to start off, I know it's kind of hard to tell, but this graph really should be starting off concave down, and then it's going to transition to concave up. So this first part is going to be concave down, so I'm going to say C down. And then this part up here on the top is going to be concave up, so C up. Okay, so that means for the inverse, the original starts concave down, which means the inverse is going to start concave up. So I'm going to try to curve it at least a little bit. So there's the first part that's concave up, and then the second part, which would be concave down. So I know the curvature is a little difficult to make obvious, but it is possible. Okay. All right. Oh, we didn't even do this top part. Okay, so kind of summarize everything. So I know that my domain of tangent is x cannot equal pi over 2 plus pi k, where k is an element of the integers. And then we're going to restrict the domain to just negative pi over 2 to pi over 2. And notice here how I wrote it with parentheses, and that's because of the asymptotes. So we cannot include the negative pi over 2 to pi over 2. And then down here, you're going to write your inverse function. You're going to write it as inverse tangent of x, or you can write it as arctangent x. So either one work. So ta-da. All right, so that's like the main part for graphing. So now we're going to actually transform these inverse functions. So these tables right here are kind of like your quick reference tables. So I kind of wrote these out for you if you want to like take a screenshot, or if you want to use this as like your little reference, you're more than welcome to. So I'm going to go down here to 7 and 8, and we're just going to kind of work on these first. So what I'm going to do is we are going to be transforming the inverse of sine. So I'm going to take my inverse sine, I'm going to just copy and paste. Okay, and I'm going to move this over a little bit so I have some room to kind of write in the table, but it's up to you on how you want to do this. All right, I'm going to make this black so we can see more color. All right, so over here, we're looking at the two transformations. So if you see anything inside the parentheses here, this is going to be a horizontal translation. So what this tells us is we're going to go right 1/2. So ignore the equation for a second. Look at just like a grid. If I'm going to go to the right 1/2, which I know that scaling is off, but it's the principle. So if I'm going right 1/2, notice how the numbers are getting bigger. So really, I'm actually going to add 1/2. So I always think of it this way. Your x is a dirty liar, do the opposite of what they say, which it applies in math. So even though your equation, it looks like it's saying we're going to subtract 1/2, you're actually going to add 1/2 because we're going to move it to the right. All right, so for example, if I was doing x plus 1/2, then I would actually subtract 1/2. And then for example, if I was doing like 2x minus 1/2, then I would actually multiply times 1/2 and then do the horizontal translation. And then if I had like 1/2 out here in the front, then I would actually multiply by 2. So it also applies to any horizontal dilations. So you always do the opposite. All right, and then in terms of the vertical translation, so we're going to go up 3 pi over 4. So your y value, you can actually take for face value. There's no special trick for it. So if I'm going up, I'm going to add 3 pi over 4. Okay, so when I make my transformations, or actually, no, we don't need the inverse. I'm just going to say x and y. All right, so now for this one, when you do your transformations, so your new table here is going to be negative 1/2, comma pi over 4. And then we're going to have 1/2, comma 3 pi over 4. And then we're going to have 3/2, comma 5 pi over 4. Okay, so now I'm going to go ahead and go plot these points. So we're going to have negative 1/2, comma pi over 4. Okay, and then we're going to have 1/2, comma 3 pi over 4. Just going to put this over here. And then we're going to have 3/2, which is 1.5, and then 5 pi over 4, which puts us right here. So it's collinear, so we're good. So with inverse sine, your graph is going to start concave down and then go concave up. So I know my graph is going to look like that. Okay, and then when you do your graph, then you are going to be expected to do the domain and range. So domain and range you can honestly just reference from your table. So my domain I know is going to be from negative 1/2 to, what is it, 3 over 2. And then for the range, once again, you can just reference your table. The minimum value is going to be pi over 4 to the maximum, which is 5 pi over 4. Ta-da! Okay, so on number 8, I'm just going to kind of get you started. I'm not going to do this one fully. So you're going to take your table for inverse cosine. All right, and then your transformations. So x plus 3/2 means I'm going to go left 3/2, which means I'm actually going to subtract 3/2 from all the x values. And then for the y values, I'm going down 5 pi over 4. So now I'm going to subtract 5 pi over 4 from all the y values. And then you can just transform the graph that way. So I'll give you all time to do that one. All right, and then a special note with tangent. So I'm not going to do this one, but I do want to mention this. When you have a vertical shift. So vertical shift or translation. So a vertical translation is going to change your horizontal asymptotes. So just make sure you also apply any vertical translations to your horizontal asymptotes that are pi over 2 and negative pi over 2. So this is going to move up pi over 2. So from pi over 2 to negative pi over 2, those original asymptotes. So when you add your new asymptotes, are actually going to be at 0 and then pi. So horizontal lines are impacted by a vertical shift. So just keep that in mind. All right, now for the next section. So I kind of spoil it up here for you, but I'm going to still go through this. So this is from the second page when we did your, when we restricted the domain. And then now I want you to kind of think of the unit circle. And it's going to give you an idea of what it's going to look like and translate to on the unit circle. So I know up here on the first few pages, we were thinking about like Cartesian coordinate grids, like your XY grid. But now for this page, I want you to think of the unit circle. Okay, so when I say the unit circle, so I'm going to kind of go through this right here. Or rather, I know this video is kind of long, so if you need a break, this would actually be a good kind of stopping place to take like a quick break. But I'm going to keep going. Okay, so on the unit circle, so we have 0, and if we go all the way around, that's 2 pi. Then up here, this would be pi over 2. And then over to the left would be pi. Then 3 pi over 2. Okay, so with inverse sine, we are restricted to negative pi over 2 to positive pi over 2. So if I were to do negative pi over 2, remember, think back to when we first learned like coterminal angles and all that. If your angle is negative, we're actually going to go clockwise. So negative pi over 2 is going to correspond with 3 pi over 2. So if I can only be in the interval from negative pi over 2 to positive pi over 2, we can only be in quadrant 1 and quadrant 4. So that's what it means over here when I say quadrant 1 and quadrant 4 only. And then the same idea for cosine. So I can only go from 0 to pi. So 0 to pi means I can only go from here to here, which means we're going to be in quadrant 1 or we can be in quadrant 2. Okay, and then for inverse tangent, so that puts us negative pi over 2 to pi over 2, which once again, same as sine, that's going to be from quadrant 1 to quadrant 4. So that's what that's going to kind of translate to. Okay, all right, now I'm going to go through this section. So for this first part, you want to think of these problems kind of like you would just the traditional unit circle. So in terms of the unit circle, you're asking yourself, where is sine a positive root 3 over 2? So sine is going to be positive, or rather, let's do theta. So sine is positive in quadrants 1 and quadrant 2. Okay, so these theta values, where the y value is root 3 over 2, that's going to be pi over 3 and 2 pi over 3. So this would be your answer if we were kind of thinking about just the unit circle. Okay, but now let's kind of look over at number 10. It's the same idea, but now because of this inverse, it's going to kind of put in more stipulations. Okay, so the way that I like to kind of think of these is we're going to think about the quadrants that inverse sine can be in, and then we're going to think about the quadrants that positive sine can be in. So keep in mind, this is a positive value, so that's where that positive right here is coming from. Okay, so inverse sine is restricted to quadrant 1 and quadrant 4. But sine is positive in quadrant 1 and quadrant 2. So what you're looking for is you're going to look for where we have a similar quadrant. So where you have a similar quadrant in these problems, that's where your answer is going to be. Okay, so over here, what I'm going to do is now I'm looking for those theta values. So this is going to happen at both pi over 3 and 2 pi over 3. But remember, we only want the value that's going to be in quadrant 1. So if I look over here, pi over 3, this value is in quadrant 1, whereas 2 pi over 3 is going to be in quadrant 2. So we completely disregard the 2 pi over 3, and we're only going to take the pi over 3. So your answer here would just be theta is pi over 3. Just that answer only. All right, so now we're going to kind of follow the same suit over here. So arc sine of negative root 3 over 2. So you're going to think about inverse sine. So inverse sine of x, that can only be in quadrant 1 or quadrant 4. And then over here, we have a negative sine value. So think about where sine is negative, what two quadrants that puts us in. So sine is going to be negative in quadrant 3 and quadrant 4. So our common quadrant that we have here is going to be quadrant 4. Okay. So what that tells us, when I look at my theta values, so my theta value here for sine being negative root 3 over 2 is going to be 4 pi over 3 and 5 pi over 3. Okay, now think of it this way. 4 pi over 3 is going to be in quadrant 3, whereas 5 pi over 3 is going to be in quadrant 4. So we want the value that's in quadrant 4, so we're going to disregard 4 pi over 3, and we want to take the 5 pi over 3. However, if you were to say your answer is 5 pi over 3, tragically, you would be wrong. And that's because, let's look at the interval. Your answer has to be in this interval from negative pi over 2 to positive pi over 2. So what has to happen? Because this angle, it's in the right area, but it's not in the right value. So what you need to do is we need to put it in the interval negative pi over 2 to positive pi over 2. So what's going to happen is we need to find a coterminal. We need to find a coterminal angle, which means what we're going to do is you're going to do that angle minus 2 pi. Okay, so over here, I'm going to do 5 pi over 3 minus 2 pi. So that's going to give us 5 pi over 3 minus 6 pi over 3, which means our theta value that we want is actually negative pi over 3. This is your answer. So I will say anytime you're going to get your pi over, or your quadrant 4s, those are going to be the ones where you're likely going to have to do a coterminal angle. Okay, so now over here, we have cosine theta, or inverse cosine, where it's positive root 2 over 2. So think about inverse cosine. Y'all, my iPad is getting hot, but it's okay. So inverse cosine is going to be in quadrant 1 or quadrant 2, since we're restricted to 0 to pi. And then this is a positive cosine. So positive cosine puts us in quadrant 1 and quadrant 4. So the common quadrant we have here is going to be quadrant 1. So when I think about my values here, we have pi over 4, but we've also got 7 pi over 4. So pi over 4 is going to be in quadrant 1. 7 pi over 4 is going to be in quadrant 4. So I only want the value that's going to be in quadrant 1, which means I'm going to disregard the 7 pi over 4, and I just want the pi over 4. Now, the pi over 4, it's in the interval from 0 to pi. so I don't have to do a coterminal angle. All right, now tangent. Okay, so think about inverse tangent. So inverse tangent can be from negative pi over 2 to positive pi over 2, so that's going to be quadrant 1 and quadrant 4. But tangent here is positive only in quadrant 1 or quadrant 3. So my common quadrant here is going to be quadrant 1. So when theta is equal to positive root 3, that's going to be at pi over 3 or 4 pi over 3. So pi over 3 is going to be in quadrant 1, whereas 4 pi over 3 is going to be in quadrant 3. So I only want my quadrant 1 value. So I'm going to disregard the 4 pi over 3, and I only want pi over 3. So that would be your answer for this one. Okay. All right, so I would suggest you pause here and actually try 14 through 16 on your own, and then you can check it. Okay, so let's go through these. So with arc cosine, so inverse cosine of x. So inverse cosine is going to put us in quadrant 1 and quadrant 2. And then I want a positive cosine x. So positive cosine puts us in quadrant 1 or quadrant 4. And my common quadrant here is going to be quadrant 1. So cosine is positive root 3 over 2 at pi over 6 and 11 pi over 6. So your pi over 6 is in quadrant 1. Your 11 pi over 6 is going to be quadrant 4. We only want quadrant 1, so disregard. And we don't need to do any coterminal on this one. All right, so I know these are kind of annoying, but it's a necessary evil. All right, so inverse sine. All right, so this is going to allow us to be in quadrant 1 or quadrant 4. And then we have a positive sine, which is going to put us in quadrant 1 and quadrant 2. So, of course, our commonality here is going to be quadrant 1. So whenever sine is equal to positive 1/2, that's going to be at pi over 6 and 5 pi over 6, which means ignore the 5 pi over 6 since it's in quadrant 2, and we just want the pi over 6. And we don't have to adjust the interval at all. So, all right, now for a tangent, I'll say the tangent ones are kind of annoying. Okay, so inverse tangent. So inverse tangent, we can be in 1 or 4. And now tangent's negative, and that's going to be a negative in quadrant 2 and quadrant 4. Okay, so our common quadrant here is going to be quadrant 4, which tells us we're going to probably have to do that coterminal. So this is going to be at 3 pi over 4 and 7 pi over 4. Okay, so we want the quadrant 4 value, so we can get rid of the 3 pi over 4. We want the 7 pi over 4. However, 7 pi over 4, we have to be in the interval from negative pi over 2 to positive pi over 2, so that tells us that we have to do the coterminal angle like we did over here. So what I need to do is I'm going to subtract 2 pi. So I'm going to subtract 2 pi. So I'm going to do 7 pi over 4 minus 8 pi over 4, which means my angle that I want is going to be negative pi over 4. This is my answer. Okay. All right, now we're going to have some fun ones. I actually like these. Okay, now for cosine, or rather, we want to find arc sine of cosine of 5 pi over 6. So you need to evaluate inside the parentheses first. So I know it's written as arc sine. I like to just write the inverse sine like this. That's just me. It's tomato, tomato. So cosine of 5 pi over 6 is going to be negative root 3 over 2. And then we're just doing the same thing that we were just doing. So we have inverse sine. So inverse sine puts us in quadrant 1 and quadrant 4. I can't write. Okay, and then we're also going to have when sine is negative. So sine is going to be negative in quadrant 3 in quadrant 4. Okay, so our commonality here is going to be quadrant 4. So when sine gives us this value, so when the y value, oh yeah, so we already kind of did this one. So that's going to be at 4 pi over 3 and 5 pi over 3. So because we want the quadrant 4 value, we can get rid of 4 pi over 3. So we want the 5 pi over 3. However, it's not in the interval from negative root, nope. Ooh, y'all, this video is long. My brain is not working. So we want to be in the interval from negative pi over 2 to positive pi over 2. So I need to subtract 2 pi. So that's going to be 5 pi over 3 minus 6 pi over 3, which is going to give you a negative pi over 3. So your theta value here would be negative pi over 3. That's a 3. Okay. All right, now let's do this one. All right, so now we want cosine of arcsine of 0.5, which is the same as 1/2. So this is the same as doing cosine of inverse sine of 1/2. Okay, so inverse sine of x, I can be in quadrant 1 or quadrant 4. That's a 4. And then sine is positive in quadrant 1 and then quadrant 2. So my commonality here is going to be quadrant 1. So then I want to do cosine of, actually here, let's scratch this. So I'm going to actually do a split. Put this one way over there. So we can evaluate cosine. So when sine is positive, so that's going to be at pi over 6. And then cosine 5 pi over 6. Okay, but here's the issue. We have to be in quadrant 1, which means I'm just going to ignore the 5 pi over 6 one. So I'm just going to do the cosine of pi over 6. So cosine pi over 6, which is going to give me root 3 over 2. So that would be your value. Okay. All right, and then tomato on 19. So I'm going to go ahead and just skip down here to these. So with number 20, 21 and 22 also. So these values are going to be a little bit more special. Aren't they all special? So these values that we give you are not going to be on the unit circle. So because these values are not on the unit circle, that means you need to draw a picture. When I say a picture, I mean of a graph. All right, so notice how your sine value is negative. So that means that we're going to be in quadrant 3 and 4. So I'm going to triangulate, which is just a fancy way of saying I'm going to draw some triangles in quadrant 3 and 4. Close enough, they're somewhat even. All right, and then the theta value we're going to focus on is going to be right here from the origin. All right, and then if we follow the negative 3 over 5 pattern, so think of SOHCAHTOA. Sine is going to be opposite and then over your hypotenuse. So what we're going to fill in, so this is going to be negative 3 on both sides and then a positive 5 on both sides. So when I do Pythagorean theorem, so we're going to have missing sides of 4 and then negative 4 over here since we're going to the left. Okay, so everything here inside the parentheses, think of this as just your picture. So this is just your setup. All right, once you draw your picture, then you need to evaluate, oh, well, we're doing inverse sine. So inverse sine, well, that can only be in quadrant 1 or quadrant 4. So because we can only be in 1 or 4, which is going to be the right side of the graph, that means we actually eliminate and cross out quadrant 3. So I eliminate this side of the graph. So we can't be that side. So then I just have this figure here, this triangle here, and now we're going to evaluate tangent of that graph. So now we're just going to do tangent of theta, which think of SOHCAHTOA, so that's going to be your opposite over your adjacent. So that's going to be negative 3 over 4. Okay, so rather, you would just need the 3 over 4, or the negative 3 over 4. Okay, now for 21. All right, so same idea, but now we're going to use some different trig ratios. Okay, so tangent is going to be positive in quadrant 1 and quadrant 3. So that's where I'm going to need to draw my triangles. So tangent's going to be positive. Actually, let's do this. So I can only do 2 lines. There we go. That's not going to be straight, but you know what? It's fine. Close enough. Okay. So once again, here's my thetas. All right, so tangent, so opposite over adjacent. So opposite, that's not a 12. Opposite over the adjacent. So opposite over the adjacent. And then when I do Pythagorean theorem, you're going to get a Pythagorean triple of 13. Okay, so here's my images. So remember, this inside right here is just my picture. Okay, and then inverse tangent tells me right here I can only be in 1 or 4. Okay, so that means I can only be on the right side of the y-axis, which means I'm going to eliminate quadrant 3. Okay, so then we're just going to do cosine of this shape right here. So when I do cosine, well, that's going to be the adjacent over the hypotenuse, which means you're left with 5 over 13. Okay. All right. So I'm going to skip 22. I'm going to go down and do an inverse problem over here. So 26. All right. So with this one, so you want to let f of x be equal to 2 cosine x minus 1. You want to find the inverse algebraically, and then you want to graph the original and the inverse, and then give the domain and range of the original and its inverse. So there's a lot on this one, but we've already done all the graphing stuff and domain and range stuff before, so I'm just going to focus on finding the inverse algebraically. But just know that in the notes and homework and whatever, you are going to be expected to do the full problem. All right, so I'm going to start with just the original. So f of x is the same as y, so y equals 2 cosine x minus 1, and then I'm going to move it down. All right, and then the whole premise of inverses is you're going to flip the x and the y, and then you're going to solve for y. All right, so you're going to treat this just like an equation. So I'm going to add 1 on both sides. So this is going to be x plus 1 equals 2 cosine y. That's a y. All right, then I'm going to multiply both sides by 1/2. So we're going to have cosine y equals 1/2 parentheses x plus 1. Now I need to get rid of this cosine to get the y value by itself. So what I'm going to do is now I'm going to take the inverse cosine of both sides. Okay, so when I do that, your cosines here are going to simplify, and then we're going to be left with just y equals the inverse cosine of 1/2 x plus 1. So that would be your inverse. So that's all I'm going to do on that problem, but just know you are going to be responsible for the rest of it. I just wanted to kind of show you what's new. But yeah, go take a fat nap. This was a lot. Bye.